Hi friends, welcome back in the second lecture on the cycloalkane, and in this lecture we are going to study the formation and chemical properties of cycloalkane. In the previous lecture we have gone through the nomenclature of cycloalkane and the meaning of cycloalkane. There are a number of methods of formation or methods of preparation of the cycloalkane. Therefore, let's begin with methods of formation or methods of preparation of cycloalkane. In this point, we will discuss four methods that are used for the preparation of various cycloalkanes. Is the reaction of carbene and alkene. Now, alkene is nothing but the compound which are having a double bond in their structure, and this carbene is nothing but it is a reactive intermediate in which carbon is a divalent and it is having two electron. So it is a reactive intermediate, keep in mind, and these two reactant, that is carbene and alkene, they undergo a cycloaddition reaction to form a cycloalkane, and generally we get a cyclopropane. Therefore, from this method we will obtain a cyclopropane derivatives. Now, to generate a carbene, we have to use either diiodomethane or diazomethane. If you look at the structure of two reactant, it is clear that there is a presence of CH2 group and other group is either I2 or N2. And these two reactants, CH2I2 or CH2N2, they decomposes within the reaction medium to form a carbene, and either I2 or N2 is eliminated. Now, how the reaction occurs? So we will take the example of alkene and carbene. And alkene, first of all, we choose a propene, and the propene I will write like this. This is a double bond in the propene, and this is the CH3 group, and it is treated with, suppose, diiodomethane. When there is a iodine, we have to use a zinc copper couple. So here there is a iodine, that's why we have used a zinc copper, and in a reaction what happens, this diiodomethane is going to convert into carbene, and this carbene then undergo a cycloaddition reaction with propene to form a cyclopropane derivatives. This is the cyclopropane, and there is a presence of CH3 group. So we get a methyl cyclopropane. So this method is specifically used for the preparation of cyclopropane derivatives. Here, look at the structure or look at the reaction. This is the one carbon, then these are the second and third carbon, and these three carbon, they undergo cycloaddition reaction. That's why we are getting here a cyclopropane derivatives. In this way, the carbene and alkene, they undergo reaction to form a cyclopropane derivatives. Now, the second example I will write here. Uh, we will take a butene, 2-butene plus. Now, uh, we can use a diazomethane. When diazomethane is used, just the reaction condition is a light or heating condition. So, in this reaction, what happens? Once again, in a C2, this CH2N2 gets converted. I will write here CH2N2 gets converted into carbene, and this carbene undergo a cycloaddition reaction to form this type of cyclopropane derivatives. These are the two methyl groups. So here we will get 1,2-dimethyl cyclopropane. Now we will see a second methods of formation of cyclopropane, and the second method is of metallic sodium and dihaloalkane. Now, before starting with this reaction, I will write one reaction that you have learned in the previous standard. Here I will write Rx plus 2Na plus R dash X. So this is the famous reaction that you have studied in the previous standard, and this reaction is known as Wurtz reaction. Which reaction? Wurtz reaction. But this is the intermolecular reaction. Intermolecular reaction. So there are two different molecules of the alkyl halides. When they heated in presence of metallic sodium, then what happens? These R and R dash, they going to combine to form a alkane. So this is the famous reaction which is used for the preparation of alkane. Now this reaction is somewhat modified, and instead of two molecules of the alkyl halide, only one molecule of dihaloalkane is used, and it is treated with the metallic sodium to form a cycloalkane. So the example I will take here, CH2, CH2Br, then CH2, CH2Br. This is the only one molecule, but it is having two halogen groups at the terminal carbon. So it is a dihaloalkane, and name of this dihaloalkane is 1,4-dibromobutane. And when it is treated with metallic sodium, two molecules of sodium, then what happens? These Br groups, they eliminated, and the bond between these two carbon is formed, and we get a CH2, single bond CH2, CH2 and CH2. So there is a cyclization of this 1,4-dibromobutane to form cyclobutane with the elimination of a sodium bromide. So this is a famous Wurtz reaction, but it is modified one. That's why it is also called as modified Wurtz reaction, or it is also called as Frunz reaction. So keep in mind, a modified Wurtz reaction or a Frunz reaction is nothing but intramolecular cyclization of dihaloalkane to form a cycloalkanes. So different cycloalkanes we can prepare by using this modified Wurtz reaction. Just you have to increase or decrease the number of carbons. Suppose I have decreases and I have written here only CH2, then CH2Br and CH2Br. So in this I have decreases the number of carbon, and when it is treated with sodium, then I will get CH2, then single bond CH2, CH2, single bond CH2 plus twice NaBr. So here I get a cyclopropane. If I increases the number of carbon, then I will get a cyclopentane, cyclohexane like this. So different cycloalkanes can be prepared by using this modified Wurtz or Frunz reaction. Then a third method which is used for the preparation of cycloalkane is a Diels-Alder reaction. In this reaction, a diene and a dienophile, they undergo cycloaddition reaction to form cyclohexene derivatives. And these cyclohexene derivatives they are reduced to get converted into cyclohexane. Now here diene, we know that the compound which is having two double bonds. But what is meant by dienophile? Dienophile, these are the compound which possesses a double bond. So this type of compound is also called as a dienophile. So we have to keep in mind dienophiles are nothing but the alkene compounds, and these two compounds they undergo cycloaddition reaction. Cycloaddition reaction, and they converted into cyclohexene derivatives. And these cyclohexene derivatives in the next step undergo reduction to form cyclohexane. So this Diels-Alder reaction it is specifically used for the preparation of cyclohexane derivatives. Now we will take the example of diene and dienophile, and in diene I will write 1,3-butadiene, and 1,3-butadiene the structure is like this. This is the 1,3-butadiene, and it is treated with this compound that is ethylene, or we called it as a ethene, undergoes cycloaddition reaction in presence of heating. So temperature is 470 Kelvin, and in this reaction what happens, this carbon it undergo reaction like this bond shifted here and it attacks on this carbon. So it is a cycloaddition reaction, and look at the structure of this butadiene. There are four carbons. Here there are two carbons. So there is a 4 plus 2 cycloaddition, and we get 6-membered ring. So I have to write here a 6-membered ring, and in this reaction this bond is shifted here, and that's why I will write a double bond here. So in the first step, we get a cyclohexene, and this cyclohexene undergo reduction in which this double bond is reduced to a single bond, and we get a cyclohexane. In this way, a Diels-Alder reaction is used for the preparation of cyclohexane derivatives. And in this reaction or in this reactant you can use a different substituent here substituent, so that we will get a different cyclohexane derivatives. Now the last methods of formation is reduction of aromatic compounds. The fourth method, reduction of aromatic compound. In the reduction of aromatic compound, we will take the example of phenol, and then we will take the example of benzene. So aromatic strategy or this method is again is used for the preparation of cyclohexane derivative. So I will take the structure of phenol. It is having a benzene ring and which is attached directly to the OH group. Then reduction of this phenol uh, in presence of hydrogen and nickel. Then what happens? This phenol which is having a aromatic ring, this aromatic ring is reduced, totally reduced. It means that all the three double bond they are converted into a single bond. So what I can write here, uh, cyclohexane and which is having OH group. So these three double bond they are converted into a single bond and we get a cyclohexanol. Now this cyclohexanol when it is heated a dehydration reaction occurs. Now look at the cyclohexanol. Here there is a presence of hydrogen. This hydrogen and this OH group it is eliminated as a water molecule and there is a formation of a double bond between these two carbon. So I will write the structure of compound and it is nothing but a cyclohexane. Now, this cyclohexane again undergo reduction in presence of zinc dust and it will form a cyclohexane. In this way, we get a cyclohexane from phenol. This is the phenol. Now, we can reduce a benzene also and in the reduction of benzene, what happens? It is treated with thrice H2, three molecules of hydrogen in presence of nickel and 473 Kelvin. Three double bonds that is present in the benzene, they are converted into a single bond and we directly get a cyclohexane. So these are the simple methods of formation of cycloalkane. Out of these four methods, one method is specifically used for the preparation of cyclopropane derivatives. Two methods they are used for the preparation of cyclohexane derivatives, whereas one method is used for the preparation of various cycloalkane derivatives. Now we will turn towards the chemical properties of cycloalkanes. In the study of chemical properties, we must know what is meant by halogenation, what is meant by hydrogenation, and what is meant by hydrohalogenation. So just we will revise this term. Halogenation means uh, addition of either halogen by replacing the hydrogen. So here halogen is added. Hydrogenation means addition of hydrogen, whereas hydrohalogenation means addition of hydrogen and halogen, that is HX. So these three reactions they are shown by a cycloalkanes. So first reaction is a photohalogenation. Now this term It indicates it is a halogenation reaction. That is, halogens are involved in this reaction, and photo light. So this reaction occurs in presence of light, in which one of the hydrogen is replaced by halogen in the cycloalkane. Here we will take the example of cyclobutane, and when it is treated with halogen such as chlorine in presence of light. So for light I will write H nu, and in this reaction what happens? There are 8 hydrogens, out of which one hydrogen is replaced by chlorine. So suppose from this two hydrogen, one of the hydrogen is replaced. So I will get here CH, then CH2, CH2, single bond, and one hydrogen is replaced by Cl. That's why I will write here Cl plus HCl. So this is the photo-halogenation reaction occurs in cycloalkanes, in which one hydrogen is replaced by halogen. Therefore, it is a substitution reaction, and this reaction occurs through a free radical pathway. In this reaction, free radical mechanism is obtained and one hydrogen is replaced by halogen. Uh, Instead of this, you can take the example of cyclopropane, and when it is treated with a Cl2, condition is light. One of the hydrogen from this carbon or this carbon, it is substituted by a Cl. So I will write here a Cl, and corresponding chloro cyclopropane, chlorocyclobutane or chlorocyclopentane is obtained if the Cl2 is taken. In this way, photohalogenation reaction occurs in case of cycloalkane. Just you have to replace one hydrogen by halogen. Then the next reaction is a catalytic halogenation. Second reaction, it is a catalytic halogenation. So it is different from photohalogenation. In catalytic halogenation, a ring breaking occurs. Ring breaking. So whatever may be the structure of cycloalkane, it is going to break into a straight chain. So I will take the example of cyclopropane. When it is treated with Br2 in presence of catalyst. Here we have taken a catalytic, that's why you have to write a catalyst. Now what happens? A ring breaking occurs and it will form a straight chain compound. Which compound? Straight chain. So uh, look at the structure of this cycloalkane. There are 3 carbon. That's why I will write here CH2, 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 because there is a ring breaking and formation of straight chain compound. Then to this CH2 I will put here a Br, and here I will write a Br. So in case of catalytic halogenation of cycloalkane, we get a dihalo compound, and it is nothing but the dibromo propane. Dibromopropane. In this way, we are getting a dihalo compound in a catalytic halogenation of cycloalkane. Now you can take a different example in which I will write a cyclobutane reaction condition. Here Br2, Fe, Br3. Just you have to write a number of carbon present in the cycloalkane in a straight chain and put a halogen at the terminal carbon. So we get a dibromobutane. It is a simple one. Just break the ring, make it straight, and put the hydrogen at the terminal carbons. Now, the third reaction is uh, catalytic hydrogenation. It is simple and it is similar to the catalytic halogenation. Just you have to write a two hydrogen at the terminal carbon after breaking the ring. So we can take example directly. Here I will write a cyclopropane plus. Here hydrogenation is there, therefore addition of hydrogen, and in presence of catalyst you can use nickel and heating condition, and in this reaction what happens, ring breaking occurs, a straight chain compound is obtained. So I will write CH2 and at the terminal I have to write one hydrogen and one hydrogen. So the overall structure it is CH3 CH2 CH3. So the cyclopropane is directly converted into the propane by catalytic hydrogenation reaction, in which ring breaking occurs and these two hydrogens they are attached to the terminal carbon of the chain. Then next example, cyclobutane plus H2, reaction condition is same, and as per our strategy I have to write a number of carbon present. I will write here terminal carbon as a C, and to this carbon there are three hydrogens. In this way, we are getting a corresponding cyclic analogs. That is, a cyclic compound is converted into acyclic analogs by catalytic hydrogenation reaction. Now, fourth reaction is hydrohalogenation. Hydrohalogenation means addition of hydrogen halide. It is nothing but HX, and in this reaction also a ring breaking take place and formation of a straight chain compound is also observed, but at the terminal carbon, at one terminal carbon hydrogen is added and at second terminal carbon halogen is added. So we will take the example once again, a cyclopropane plus here HBr, that is HX, hydrogen halide. When they are heated together, what happens? It is going to add with one terminal carbon, and this Br it is going to add to another terminal carbon. That's why I will directly write here CH3 CH2 CH2 Br. So in this way we will get a corresponding alkyl halide by hydrohalogenation reaction. Here name is propyl bromide. If I take a cyclobutane, then addition of HBr it gives CH3 CH2 CH2 then CH2 and Br. In this way we are getting hydrohalogenation product as a alkyl halides. So I will write here butyl bromide. And the last reaction which is shown by cycloalkane is action of heat. Now, action of heat means when the cycloalkanes are heated, what will happen? So I will take the example of cyclopropane. When it is heated in presence of catalyst platinum, then once again a ring breaking occurs, and with the formation of a straight chain compound, but this straight chain compound contains a double bond. Which bond? A double bond. So keep in mind, in action of heat, ring breaking also occurs with the formation of straight chain compound, and but the straight chain compound is having a double bond in the structure. Now, in this structure of cycloalkane, there are three carbons. So I can write here carbon, single bond, carbon. And in this compound, there are six hydrogens. How many hydrogens? Six hydrogens. These six hydrogens, they remains as it is, but they are rearranged with the formation of double bond. Suppose I have written here a double bond. Then this carbon has two hydrogen, this carbon has one hydrogen, and this carbon has. In this way, after heating a cyclopropane, we get a CH3, single bond CH, double bond CH2. The number of carbon, number of hydrogens, they remain same, but there is a formation of double bond within the compound. Now, consider a next example, that is a cyclobutane. When it is heated, what will happen? First of all, we will write here four carbon chain, and in this compound, I will put a double bond. Now this carbon, it is having three hydrogens. This carbon, it is having one hydrogen. Here I will write one hydrogen, and here I will write three hydrogen. So the structure will be CH3, CH, double bond CH, then CH3. So the cyclobutane is converted into 2-butene, whereas cyclopropane, it is converted into 1-propene. So the action of heat gives a alkene. Which compound? Alkene. In this way, we have studied the different chemical properties of cycloalkane, such as photo-halogenation, catalytic halogenation, catalytic hydrogenation, uh, hydrohalogenation, and action of heat. Out of these five chemical properties, four properties involves breaking of ring, whereas only one property, that is photo-halogenation, involves substitution reaction in which one hydrogen is replaced by halogen and the cyclic structures remain as it is. Now we will see what we have learned in this lecture. That is, we are going to revise the points that we have learned in this lecture. We will summarize this lecture. In this lecture, we have studied different methods of formation. First is from carbene and alkene, second sodium and dihaloalkane, third by Diels-Alder reaction, and fourth reduction of aromatic compound. Here you can see this is the alkene, and this reagent, it generates a carbene in a situ. In place of this reagent, you can use diazomethane, which also generate a carbene. This carbene undergoes cycloaddition reaction with the alkene to form cyclopropane derivative. In the second methods of formation, dihaloalkane, when treated with sodium, it will form a corresponding cycloalkane derivative, and the structure of cycloalkane depends upon the number of carbon present in uh, dihaloalkane. Whereas in third and fourth methods of formation, we generally get a cyclohexane derivative in which first step there is a formation of cyclohexene, which is uh, having a double bond in their structure and undergoes a reduction to form cyclohexane derivatives. Either reduction of phenol or benzene take place, or cycloaddition reaction of this uh, butadiene and ethene, that is diene and dienophile, take place to form cyclohexane derivative. This is all about the methods of formation of cycloalkanes. Now, in the chemical properties, we have studied a photohalogenation, catalytic halogenation, catalytic hydrogenation, hydrohalogenation, and action of heat. All these reactions are summarized in this picture, in which you can see here, in photohalogenation there is a replacement of hydrogen by Cl, whereas all other reactions, they involves a breaking of ring, that is ring breaking occurs with the formation of corresponding product. In the halogenation we get dihaloalkane, in hydrogenation we get alkane, in hydrohalogenation we get alkyl halide. But when a cycloalkane is heated, we get a alkene molecule. Finally, I will wind up this lecture. Thank you. Thanks for watching E-CHIMICA.